Okay, gentlemen, today we got a really short video talking about concavity. So just to really quickly debrief what we were talking about with increasing and decreasing, we basically said as we go from left to right, if our y value is going up, we're increasing, and if our y value is going down as we go from left to right, we're decreasing. But I also want to talk about how fast we are increasing and how fast we are decreasing in certain problems. And that's what concavity talks about. So the definition of concavity, it has a more technical definition because it's more of a calculus topic, and that uses some calculus materials as well as language and definitions. But for our intents and purposes, what it does is it describes how the slope, the rate of change, ROC, rate of change. I'm probably going to abbreviate this a lot from now on and just write ROC. So it describes how the slope changes over time. So for example, are our slopes getting bigger? Are our slopes getting smaller? Is it growing faster? Is it growing slower? We know already, there's a few points, and these are all things that we need to take down. If a graph has a positive slope, it's increasing. So for example, if I'm thinking about y equals mx plus b, and my m is 4, we know that we're increasing, and vice versa. So those are just good points to have. And here are the two big ones: concave up and concave down, what this looks like and what this is. Now, if over time our rates of change are increasing over time, so as we go from left to right, we see that the rate of change over time is increasing. We know that our slopes are increasing over time, and what we do is we call that concave up. And I'm going to skip down before I get too much into it, and we're going to talk about what's called this tangent line. So what the tangent line is, a line that touches a graph one time, and it approximates the slope at a point. So if I take the tangent line of any function, I'm drawing a straight line that touches the graph only once. So if I go over here to this concave up situation, this is what it looks like. And if I were to take a bunch of tangent lines and approximate the slope, let me do it in actual color. What do we notice over time? Right here, the slope is really negative. We're really negative. Over here, the slope is still pretty negative. Over here on the bottom, my slope is 0, actually. And then over here, it's kind of positive. And then it's really positive here. So as I go from left to right, our slopes are increasing over time. And your shape of the graph is going to look like this. I'm going to say this looks like a smiley face. So this looks like a smiley face. Kind of opens up. Other people will say it kind of looks like a cup or a bowl or that sort of thing. Or maybe it looks like a valley because it's got the two walls on the side and it looks like a valley. And a similar line of thinking, concave down, would be that the rate of change is decreasing over time. The rate of change is decreasing over time, which means the slopes are decreasing over time. So if I do kind of the same thing with those blue lines here, that's concave down. The blue lines would say over here, I'm super positive. And then I get a little bit less positive here. And then I get to 0. And I'm talking about the slopes. And then I start going downwards. I start going negative. And then I start going more negative. And then I start going super duper negative. Over time, my slopes are decreasing as I go from left to right. So I say slopes are decreasing, and what I like to call this is, the other one is a smiley face or a happy face. This one is a frowny face. So that's kind of the language that I'm going to use when we're looking at these different slopes. I'm going to say, hey, do we have a smiley face? Do we have a frowny face? That will tell me whether it's concave up or concave down. The last little note that we have is that a point of inflection is the point where concavity changes. And I'm going to come up and we're going to talk about this piece a little bit more. But for now, make sure we get this down and just know that, that it is where concavity changes. The other thing to note is that this point also has a characteristic that it's going to have the steepest slope. So let's go ahead and answer a couple questions. I give you a scenario over here. Please draw this in your notes before you go ahead and listen to this part of the video. So the first thing that I want to do is answer is f my function. So if I have this fancy curly f, that's talking about my function. Is it increasing or decreasing at x equals -1? So what I'm going to do is I'm going to find x equals -1, and I'm going to go up to my function. And what I'm going to do is I'm going to draw that tangent line right here. And we could see that slope is positive. It's going up from left to right. So I could say it's increasing, and the reason why is our slope is positive at x equals -1. So now the reason I ask you this question first is I don't want you to get it confused with question number 2. Question number 2 says, is the rate of change of our function increasing or decreasing? So essentially, we could rewrite this in a more English way as, are the slopes of f increasing or decreasing over time at x equals -1? So what's going to happen is I want to basically look if I'm concave up or concave down when x is equal to -1. And I'm going to do this 2 separate ways. One, we're going to analyze the slope, and one, we're going to analyze the concavity, show that it's the same thing. So we can see here on this portion of the graph, this whole entire portion up till about here-ish, we could see that I'm concave down. I have that frowny face type of shape. Now that is opposed to, on the left, we could see I'm opening up. I have that smiley face type of shape. I'm happy. So what does concave down tell me? Concave down tells me that my slopes are decreasing. We could remember this. My slopes are decreasing. It's concave down. So my answer can be as simple as my rate of change is decreasing at x equals -1, excuse me, because f of x is concave down. So what I'm looking at here is this frowny face action here, and that's going to tell me whether my slopes are increasing or decreasing. Next question. Which interval of my function is increasing and decreasing? So this is just talking about going up and going down. This is not concavity. That's going to be a later question. So this is saying when I'm going up or down. So this is going to look quite like the question, the sign question we did 1 or 2 days ago. So we can see here I'm going up till about here. I'm going up, and then I'm going down, and then I'm going back up. So I could say from -infinity to about 0.5, or -0.5, I should say, we're going up. So let's say I'm increasing on -infinity to 0.5 negative. Now, it's important that these are indeed parentheses. I don't want brackets in this case. I'm not allowed to touch infinity. It's a concept. And I don't want to touch 0.5 because the slope here is technically 0. It's not increasing or decreasing. My next interval would be from like 0.5 to, we could just call this 2 to make it simple. So I can say we're decreasing on -0.5 comma 2. So on that interval. And then lastly, as I go from 2 on up to infinity, I'm increasing again. So comma 2 and infinity. Now, estimate the point of inflection. Let's go ahead and talk again about what the point of inflection is. It is the point at which concavity changes, and it also has the steepest slope. So let's keep those two things in mind as we answer this question. So we kind of talked about briefly before that it looks like we're concave down here till about here, and then it switches and we start to get that smiley face. So right about here is going to be where concavity changes. We can see how we go from down to up. Now this point also we could see has a really steep slope compared to the ones around it. You see it's not very steep, not very steep, and then it gets really steep here, and then it starts to kind of flatten out again. So somewhere around here, we could just call it 0.5 would be my point of inflection. So x equals 0.5, and the reason is concavity changes, and we have a large slope, or I want to make sure I get the wording exactly right. Steepest slope, that's what I use. And it has a steepest slope. So we've talked about this last question a few times now. On which interval are we concave up, concave down? I'm just going to draw it in highlighter for one last time. We said that this interval is concave down. Right about here is our point of inflection, and then we are concave up going this way. So we're concave down, and then concave up. So I'll leave that up for a second, and then we'll go ahead and write those intervals at the bottom. We're going to notice that that point of inflection is at 0.5, so our intervals are going to kind of surround there. So I'm going to say we are concave down on negative infinity to that positive 0.5, because that's where that concavity changes. And we're concave up on 0.5 to infinity. So that rounds up everything that I want to talk about today in terms of concavity. Tomorrow, what I want you to be prepared is we're going to answer multiple questions that look something like this, where I ask you stuff about increasing, decreasing, concave up, concave down. Those are the 4 things that we're going to be working with extensively, and we're going to have a quiz on that later on this week. So have a good rest of your day.